In this goal, we will learn the difference between ionic and covalent bonds, and also we will classify covalent bonds as being polar covalent or nonpolar covalent. So first of all, ionic versus covalent. Except for a bond between two non-metallic atoms of the same element, every bond has some ionic and covalent character. And there's an arbitrary cutoff line for when we call it covalent or ionic. So for example, on this little chart, we have this little HF right there. Notice it's just barely over the line. So it's classified as covalent, but it has a lot of ionic character because it is so close to that line. So what I'm saying here with character is how to describe the bond. Everything has a little bit of transferring of electrons and a little bit of sharing of electrons. And this HF, we see that it's mostly sharing, but we see that it just barely fits over that arbitrary cutoff line. So how can you tell if something's ionic or covalent? The general trend is that ionic bonds are between a metal and a nonmetal. So on your periodic table, you would look up the elements in the bond and see if they are metals or nonmetals. If you have a metal with a nonmetal, it will be ionic. If you have two nonmetals, it would be covalent, and a metal with a metal would be a metallic bond. Bonding is based on electronegativity, and electronegativity is defined as an atom's pull on the electrons in the bond, and it is an arbitrary number system that has no units, with fluorine as a 4, and the trend is as I go left to right towards fluorine, we have an increase in electronegativity, and we see as we go up a family that it also increases. Also notice that metals have a very low electronegativity and nonmetals have a very high electronegativity. And this is because metals tend to lose electrons. So if you're looking at an atom's pull of electrons in the bond, the metals aren't going to be pulling, they're going to be giving their electron and letting the nonmetal pull it away. So the nonmetals, they have a tendency to gain electrons. So they're going to be pulling the electrons in the bond, and there's going to be a transfer if it's between a metal and a nonmetal. But this is your trend right here of electronegativities. This is listed on your periodic table, but the very back of your periodic table, and it will be the upper black hand corner, the upper right hand side. You will find that electronegativity value. The electronegativity difference determines the bond type. If there's a great difference between the electronegativities, then it would be classified as ionic. If there's a minimal difference in electronegativity, then we would classify that bond as being covalent, or it's sharing electrons. And you can look up the numbers and subtract them. The dividing line between covalent and ionic is 1.7. Equal to or greater than 1.7, it's ionic. Less than 1.7, it's covalent. These numbers, however, are not going to be on the AP test, so you shouldn't classify ionic versus covalent by always looking up the numbers. You should be able to look up and see if it's a metal or a nonmetal, or two nonmetals to classify ionic or covalent. Let's look at this first one. So we have sodium with fluorine, so that's a metal with a nonmetal, so I would just say ionic. But you could look up to see how ionic by subtracting their electronegativities. If you subtract and get a negative number, just make it positive, but we see that this is very ionic because it's way above the 1.7. So again, this is a transfer. The sodium valence electron is going to be transferred to the fluoride ion. Let's look at the next one. We have two chlorine atoms, and this is the only case where there's no ionic character. I have only a pure covalent bond, and this is when it's bonded to itself. So we can look up the electronegativity values, and of course they subtract, we get 0. This tells us that's pure covalent. 100% sharing. There's really no difference in electronegativity, and because of that, it's 100% sharing, no ionic character. If you did have two nonmetals that weren't alike, they would still be sharing, but they would have a small difference in electronegativity. This just explains what I've been talking about, difference between ionic and covalent. Covalent, they have a very small difference in electronegativity, so you're sharing electrons. Ionic, metal with nonmetal, a big difference, and so there's a transfer of electrons. So in covalent bonding, it is with nonmetal and nonmetal. They're sharing electrons, and down below, this is a CO2 molecule. Notice that we've drawn those Lewis dot structures. Carbon's dots are actually little X's, so you can see that they come from the carbon, but they will fit together kind of like a puzzle, and they will share their electrons. And notice that now oxygen has 8 valence electrons, and this one also has 8. And carbon, it is also sharing. So it came in with 4 valence electrons, but with sharing with the oxygen, it now has 8. So this is satisfying the octet rule. Covalent bonds can be further separated into polar covalent and non-polar covalent. And we're usually lazy and just say polar and non-polar. So when you hear those terms polar, non-polar, it's always a sharing situation. It's always a covalent bond. You can use the numbers to subtract to figure out if it is polar or non-polar, and a difference of 1.4 equal to that or less, that would be non-polar covalent. So you can see that the difference is hardly anything at all, and that means that it's non-polar. And polarity means that you have a positive area and a negative area. So if it's non-polar covalent, that means there's equal sharing and there's not going to be any positive or negative areas. It's going to be just all the same. Polar covalent, you would have areas where it's a little bit positive and a little bit negative, and you could draw it like this with the electron clouds spreading out just a little bit and showing that it's a little bit negative here and it's a little bit positive here, but they are sharing electrons between the two. And then ionic, of course, that's when we have complete separation of polar and nonpolar. And so we have electrons are taken from the metal and given to the nonmetal. All right, so how can you tell if something is nonpolar or polar? Well, you need to memorize what is nonpolar. So there's just really 2 rules to know. And the rules is for nonpolar covalent, if it's bonded to itself or it's a carbon-hydrogen bond. So you need to know anytime you see a carbon-hydrogen bond, it is nonpolar covalent. That means that polar covalent would be everything else. So everything else that it's not bonded to itself and it's not a carbon-hydrogen bond, it's going to be polar covalent. And then watch out for ionic. Ionic is still a metal with a nonmetal. So again, your nonpolar covalent and polar covalent, this would be a nonmetal with a nonmetal. And memorize the 2 situations where it is nonpolar. And here again is what you need to memorize. Memorize what's nonpolar, and then everything else will be polar. And then if there's a metal and nonmetal, it will be ionic. We do describe ionic as being polarity, but it's just extreme polarity, and so we call it ionic instead of being polar. So again, you don't need electronegativity data to subtract to see if it's polar or nonpolar. You're just going to look on your periodic table. If it's ionic, this will be a metal and a nonmetal, and they'll be far away from each other on the periodic table. So the closer they are to each other on the periodic table, that's going to describe the more covalent it is. So covalent, again, nonpolar covalent, you need to memorize it's the same element or carbon-hydrogen bond. Polar covalent would be everything else, and it would be both nonmetals, or in just a sec I'll talk about you can have small metals with large nonmetals. This would be an exception. I don't know if they really would ask that. And then, of course, metallic would be metals with metals. So together, let's classify these following bonds as being ionic or covalent, and if they're covalent, if they're polar or nonpolar. Let's start off with this first. We have sulfur and oxygen. I'm going to look on the periodic table. On the periodic table, I see they're on the right-hand side. They're both nonmetals. And they're not nonpolar because they're not bonded to themselves and they're not carbon and hydrogen. So this would be polar or polar covalent. Let's look at the next one. Carbon and hydrogen. You should have this one memorized. This one is always nonpolar. So the difference between carbon and hydrogen is very, very little. As far as electronegativity goes, even though hydrogen is way over on the left above lithium, imagine for electronegativity, for bonding, that hydrogen is right by carbon. So if you ever have a carbon-hydrogen bond, remember that will be nonpolar. This next one, we see that it's bonded to itself. And so this would also be nonpolar because that's one of the situations for nonpolar, bonded to itself. And it doesn't matter if it's double bonded. Double bonded, single bonded, it's going to be nonpolar. So it's going to share equally. This next one, I have a metal with a nonmetal. They're going to be far away from each other, have magnesium It's an alkaline earth metal. It's over on the left-hand side, and oxygen's over on the right-hand side. They're far away from each other. Their difference in electronegativities is going to be great. So they are going to be polar. So they are going to be ionic. And remember, ionic is extreme polarity. So the magnesium will be positive and the oxygen's going to be negative. Let's look at the next one. So find where these are, and one can really trip you up. So notice it's not ionic. This is a metal with a metal. So this would be a metallic bond. So as mentioned before, you can have a small metal atom and a large non-metal atom come together and give you a polar bond. And that's kind of an exception here because, again, as you go down the periodic table, it gets smaller as far as the trend. And if I have something at the top, the metals, if you put these two together and you subtract their electronegativities, you see that you get a difference of 1.5, which would be on the polar covalent category, but just barely so. And this is kind of more of an exception, but it is out there, so I thought I'd teach it to you. So have you tried this one. So stop the video and see if you can classify each of these as polar or nonpolar. Okay, we're back. So this first one, you should have this one memorized. This one is nonpolar. This next one, we have it's bonded to itself. This is the other situation where it's nonpolar. And then on the third one, we have carbon with chlorine. When I look at the periodic table, we see that they're both non-metals. It is not bonded to itself, and it's not carbon-hydrogen. So those would be our nonpolar situations. So this one is polar. We can use an arrow to show polarity. So as far as electronegativity goes, the chlorine is a little bit more electronegative than the carbon. And so because of this, I can draw an arrow pointing to the chlorine saying, hey, this one has more electronegativity. And then I put a little plus sign over here, and this is showing that the carbon has less electronegativity in comparison. Another thing that you can do is you can draw little delta signs. So they look like really funny S's, but this is a lowercase delta symbol, and I just put a little negative on it. That means on this side of the bond, it's a little bit more negative. So those electrons, they travel between the two atoms. That's what a bond definition is. And those electrons will spend more time around the chlorine because it's more electronegative. And so we can show this by doing the little delta minus sign. If there's a delta minus sign on the other side, I can put a delta plus sign over here, showing that most of the time the electron in the bond is not going to be with the carbon. So that will leave overall a polar situation, a little bit positive on the carbon side and a little bit negative on the chlorine side. Let's look at the last one here. We have potassium is a metal, and this is a nonmetal. So this would be ionic. And where it is also polar, but it's a transfer. So this one is completely negative, and this one is completely positive. And that's why they're sticking together. That's the definition of an ionic bond. Here's a picture that shows the electron clouds in nonpolar covalent, polar covalent, and ionic. And you can see in the nonpolar how it's sharing the electrons in the bond, because you can see the electron cloud distribution is the same. And in the second one, this one is polar. You can see the electron cloud distribution is shifted over on one side. So it's a little bit negative here and a little bit positive here. And I could draw the little arrow. Looks like that. Okay. So again, the arrow points to the more negative side. And let's look at this next one. So this one is ionic. We can see a complete transfer. So it's a little bit, or it's completely negative here, and it's completely positive here. Okay, so again, ionic is also polar, but it's so polar we say it's ionic. There are many different names for polar. Polarity just means that there's a positive side and a negative side. It is also described as a net dipole, and sometimes they give a number measurement. So the higher the number, the more polar it is. The lower the number, the less polar it is. And then we have dipole is another name for polarity. And sometimes they call it a dipole moment. And that's because that electron, again, is being shared between the two atoms. And if it's over on one side at one moment, then that shows that it's more polar at that one moment. But These all mean the same thing. They all mean that they have a little bit of a positive side and a little bit of a negative side. One thing you should know is the larger the difference in electronegativity, then the stronger the dipole will be. So in other words, the more polar it will be. But don't freak out if they have some different names that they describe polarity, especially if they say dipole. Dipole just means two poles, or it's polar, a little bit positive on one side and a little bit negative on one side.